Hello, my name is Stephen Villanueva Jr., an astronomy graduate student at The Ohio State University. I'm here to talk about my recent paper, The Dedicated Monitor for EXotransits, Demonex, 7 Transits of EXO-4b, a paper I submitted with my collaborator Jason Eastman and advisor Scott Gowdy. This is the first data release of the Demonex telescope and contains 7 new transits of the misaligned hot Jupiter EXO-4b. Hot Jupiters are a unique class of extrasolar planets known for their large Jovian masses and close proximity to their host stars. The discovery of hot Jupiters has challenged our thoughts on what solar systems are thought to look like. Understanding these systems will help better constrain our understanding of planet formation, disk formation, and planet migration. For hot Jupiters that happen to pass in front of their host star, or transiting systems, a number of methods can be used to understand these planets. In the case of transits, when a planet passes in front of the host star, the planet blocks some of the light. This is shown in this cartoon from WIN 2010. The depth, duration, time of ingress and egress, and other properties of the shape of the transit light curve allow us to infer the density of the host star, as well as a number of geometric ratios relating the planet to the host star, but all of these are in terms of the host star's radius. If we combine this with radial velocity measurements, or a constraint on the mass and radius of the host star, we can get the properties of the host star and planet in terms of physical units, not just ratios. To make these measurements, we use archival radial velocity and transit data combined with new transit data from the Demonex telescope. Demonex was a 20-inch automated and robotic telescope that operated at a Weiner Observatory in southern Arizona. Demonex was designed to monitor stars known to host transiting hot Jupiters. For over 3 years, Demonex monitored and collected light curves for over 40 transiting hot Jupiters. We first look at 7 new transits of EXO-4b taken with the Demonex telescope. The best fit model is shown in red and plotted over each individual light curve. Individual time series flux measurements are shown in black, and their error bars are plotted in gray. We were able to obtain 3 nights of full transits containing both the ingress and the egress. 4 nights, however, contain only the ingress or only the egress. Both of these still provide useful information. Detrending is a common practice amongst ground-based transit groups. Here we've analyzed Demonex data 8 times using different possible combinations of commonly used detrend parameters. Plotted here are individual inferred values and the 68% statistical uncertainties. For reference, the solid and dashed lines are previously quoted values from a 2010 Narita et al. Study of EXO-4b. In many cases, the inferred values are consistent with any errors of previous results, regardless of the number of detrend parameters or choice of detrend parameters used. However, we do note that as more detrend parameters are included, the values become more consistent. We do note the systematic offset in period between our sample and the Narita sample, as expected when analyzing different individual light curves. One worrisome feature, however, is that the radius of the planet to the radius of the host star, RP over R star, can vary by more than 3 times the quoted statistical uncertainty depending on the choice or combination of detrend parameters. This is an indication that there are large systematic errors present in our data that are currently unaccounted for. This worrisome trend is also present in the inferred values of the central transit times. Here, for each of the 7 nights, we have plotted the expected central transit time versus the observed central transit time. We would expect each night to be consistent with 0 if there were no transit timing variations. Even with detrending, many of the Demonex nights are still consistent with the presence of a transit timing variation. However, depending on the choice of detrending variables, the inferred central transit times can vary by over 1 sigma. Because of this, we do not believe these transit timing variations are real, but instead due to unaccounted for systematic uncertainties. Thus, one should exercise caution when trying to infer the presence of additional planets using these results. With no clear choice on which set of detrend parameters is the correct set, we instead opt to use as many detrend parameters as possible. We do note that air mass and time are correlated, and opt to use only one of these 2 detrend parameters. We then move on to our global analysis, detrending Demonex data against X, Y, and time. We combine our detrended Demonex data with other available datasets to analyze EXO-4b in a homogeneous manner. Our global data set includes archival data, some of which is public and some of which was provided to us kindly by various authors. The final global data set contains 24 light curves of EXO-4b. Along with the transit data, we simultaneously fit the radial velocity measurements from McCullough 2008 and Narita 2010. Because the Narita 2010 radial velocity measurements were taken during transit, we separate this data for the purposes of error scaling, but now must also include the Rosser-McLaughlin effect. We investigate two possible Rosser-McLaughlin models, those based off of Oda et al. 2005 and 2009, and those described in Hirano et al. 2010. Due to the way that we scale our errors, both models fit up the data equally well, but do so with very different inferences for the spin-orbit misalignment lambda. The two methods, one an analytic formula and the other based off of cross-correlations with stellar template spectra, find very different values for both the stellar spin v sin I and the spin-orbit alignment lambda. Gowdy and Wynn have shown that there's a strong degeneracy between v sin I and lambda for systems with low impact parameters, as is the case here. Other studies have shown that the Oda et al. Analytic method can systematically misestimate the amplitude of the Rosser-McLaughlin effect. Combined, this can lead to a misestimation of the spin-orbit alignment lambda. Because of this, we use the Hirano-based models instead. After considering and fitting all of the available data with all of the available models, we arrive at our final results. We provide an updated transit ephemeris for EXO4b by fitting all 24 individual light curves for their central transit times. We also present the results of the global fit. These include updated masses and radii of the host star and planet. These go along with updated planetary parameters, stellar parameters, RV parameters, and transit parameters from EXO4 and EXO4b. We also confirm the model-dependent spin-orbit misalignment of EXO4b and make note on the differences between the two Rosser-McLaughlin models considered here. Of course, all of these inferences are based off of the choice of detrending parameters used. This is a common practice amongst ground-based transit groups, so care should always be considered when making inferences or quoting detrended data, which is common throughout the literature. Finally, I want to thank you for your time, and I hope you enjoyed this Ohio State Astronomy Coffee Brief.